Hi, we're going to talk about surface hardening of steel. So for this case, only the surface is to be hardened. Okay, so the surface is to be hardened, and there's no change in the core. So the core is the same. So why you want to do that? Because the core, which when it's soft, the core is soft. Okay, so you have a soft core, is able to absorb impact energy. As we mentioned before, soft is ductile, hard is brittle. So for this case, you want the surface, okay, of the cam. So you have a cam down here, and you have gears over here. So you want the surface, okay, to be hard, to have better wear resistance. However, you like the core, right, the core to be soft, right? And why you need to be soft? So you can absorb impact energy. Okay, like gears, if you engage the wrong gear in your car, you have impact energy. Okay. So surface hardening are classified as there are two types: selective heating of surface and alteration of surface. Okay, so we go for selective heating technique first. So the most easiest one, the most usually used are flame heating. So it uses oxyacetylene flame to raise the surface temperature to form austenite. And so once you heat it with austenite, you quench it in water or oil to form martensite. Okay, so but you have to heat up to austenite first. So then you temper to reduce the hardness to the desired. So tempering is just to reduce the hardness, no change in microstructure, and then you control the depth of the martensite. However, flame heating, controlling the depth of martensite is always difficult. So this is the frame. You can see, as I said, I don't enjoy teaching this, but the outer layer of the cone is 1275. The white is 3100. So if you look at steel, okay, so when you do surface hardening, you usually need to achieve, depending on percentage of carbon, you usually want to make sure that it's all in the austenite region. Okay, so you use a flame to do it. The other one is induction heating. So how does induction heating? You can YouTube this. Is you have high voltage supply passing through a conductor coil, right? So you generate thermal EMF. So you can heat up the workpiece, and in the center over here, this is your workpiece. So this technique, known as the induction heating, is really is generated by high voltage supply, will generate intense EMF, electromotive force, to heat the material. So the material is placed in a conductor coil, as you've seen before, and the thermal electromotive force will increase the surface temperature. So the heating rate is pretty high, 200 to 500 degrees C per second. And the rate of heating is controlled by adjusting the voltage and also the frequency of the power supply. It's usually used on cylindrical and non-ceramic. Okay, cannot do for non-conductive materials. And the really good side of this heating method is it's able to control the depth of heat penetration with good accuracy, repeatability. Means you do it 10 times. Good accuracy means if you want the depth to be like 4 microns, you always get about 4 microns depth. Repeatability, if you do it 10 times, okay, you always get that same depth. Okay, whereas accuracy, you can get 4 microns, 3.95, 4.101. So, okay, so sorry, 4.01. So the accuracy is good. Now, the other way to do surface hardening is altering the surface chemistry. Okay, so one way is to do carburizing. So the diffusion of carbon into the FCC. So now again, you have to heat up the FCC phase at elevated temperature. So carburizing, you can break down to gas carburizing, which is surround the part with hot gas, or liquid carburizing, where the steel is placed in a molten bath with carbon. So this is the liquid is much faster. So example, like what we have spoken before, if we were to normalize steel at 0.3%, okay, so 0.3% is at your core, surface is still 0.3, but you get a what? thin layer of martensite. However, if you want to increase the thickness, the surface has to be carburized up to 0.8% carbon. We'll talk to you why 0.8. So when that's the case, your core is still what? Soft at 0.3% carbon with perlite and ferrite, but the surface now will have 0.8% carbon. This will generate a thicker layer of martensite. Now, why we want to keep it at 0.8? Because if you look at the phase diagram now, if carbon at 0.8 is in this region, the highlighted region, so what you realize over here is the temperature to heat austenite is at its lowest. Okay, so theta austenite, right? It's at its lowest, right? If we look at this part, right? To heat single phase austenite, that's the lowest region. So less heat or less energy is required, and upon quenching it will not crack. So that's what I've written down here. So when carbon is between 0.77 to 0.83, the temperature required to obtain single phase austenite microstructure before quenching is at its lowest. This will prevent cracking of the component in quenching and consume less energy during heating, and also part distortion. Okay, so for this part, this is what you have to learn regarding surface heating technique.